The ideas expressed in the following presentations are those of the speakers and do not necessarily reflect the views of ACI or its committees. ACI web sessions are recorded at ACI conventions or other concrete industry events and will be made available for viewing free of charge for 1 week. Thereafter, they will be archived on the ACI website or added to ACI's online CEU program, depending on their content.
Dr. Taylor has been employed at the National Concrete Pavement Technology Center at Iowa State University for 7 years. During that time, he has been involved in managing and conducting several research programs, investigating materials related aspects of concrete pavements. Dr. Taylor is actively involved in teaching applied concrete materials technology to practicing engineers. He is a professional engineer. He's registered in Illinois. He is president-elect of the ACI Iowa chapter, board member of the ISCP and TERA. He is active in TRB and ASTM and ACI.
Thanks for the opportunity. It's kind of fun to sort of wrap up a fairly broad range of presentations, and I'll try and address some of the questions that have come up. First thing I have to qualify, all of these slides are actually developed by Bob Dawson from the Iowa DOT. So if there are any hard questions, call Bob. He was the original person that was invited to come and do this talk, but he couldn't get the travel arrangements. So I'm it. And the reason we're addressing this is that Iowa thinks we've got it. And in a way, I think we have. Is the DOT has a fairly rigorous approach to assessing and accepting aggregates for their system. And that's the details that we'll go through in the next few minutes. The history is, again, early 50s, 60s, 70s, started to work out. There was a problem. The freeze-thaw approach kind of sort of didn't work. And so a couple of guys in the DOT got together and started to look at, well, what are the common features of the systems that are working and the ones that are not working? And it seemed to them to come out to be a combination of the pore size issue and some chemical effects. One of the reasons that it is kind of entertaining is that Iowa is not a simple set of geology. And again, I'm an engineer, not a geologist. So I'll talk about the slide very quickly and move on. But, you know, there's lots of pretty colors, and they're all different.
Oh,
Meaning...
Really?
See, engineers can talk. You know, we're dealing not only with pure limestones. We've got mixtures. We've got, you know, fairly high dolomitic materials, and we've got a whole range of stuff in between. The short answer basically is the good stuff is up in this corner, and the bad stuff is down in this corner. And again, you know, we're also getting some materials coming in from the Minnesota side, which are glacial mixtures. So, you know, you're getting a pile of stuff from, you know, it's rounded, it's been beaten up by the glacier, but it isn't a pure material. It's got all sorts of jumbled stuff in it. And that's part of the work that's still ongoing. So again, we've already heard a lot of information about what it typically looks like, how quickly it starts to fall apart. You know, again, the same sort of numbers as that, you know, Tom and Randy have talked about is, in 15 to 20 years, it starts off with the staining, and then the cracking develops, and it's not very pretty. This is one that hasn't been talked about. The de-icing salts seem to make it a little bit worse. Again, images that are not very different. Somebody was asking a question, how do we tell if it's a decracker or a paste-based issue? To my mind, it's pretty simple. On the outside, Tom already referred to it, that, or maybe it was Randy, was, you know, the cracking format is slightly different. You know, if it's an aggregate-based issue, it tends to spread further and further away from the joint. If it's a paste issue, it tends to move a little bit more slowly. But really, the fundamental test is cut it in half and put it under a microscope. if the cracks are in the aggregate, it's an aggregate problem. If the cracks are in the paste, it's a paste problem. And if you want to learn about that one, you've just missed a really good session 2 doors down. Because that is, the topic of the work that I've also been involved in is looking at what's causing the paste to fall apart. And Jason and Larry and all the smart scientists are talking in another session. So again, we'll focus a little in here on the aggregate side of the game. The DOT adopted a number of different classes, and this is basically based on experience. How long did things last before they started to go to hell? And they came up with these different classes. Basically, the bigger the number, the longer we would hope the system is going to last. Then they started working on what are the test methods that tie together with this performance. One of the ones, again, was sort of hinted at in one of the earlier presentations is that Wendell DeBerkey came up with this concept that it is the range of the pore sizes in the aggregate that is critical. And we can explain that because if you think about your bath sponge, the holes in that sponge are pretty big. You can get the water into the sponge. You can get the water out of your sponge. It's all pretty easy. You pick a sponge out of your bath and it runs pretty quickly. Don't have to leave it long, and it's reasonably dry. Big pores, water comes in, water goes out, who cares? Very small pores, the water doesn't get in at all. No problem, because if we haven't got critical saturation that Tom referred to, we don't have an issue when freezing occurs. However, there is this range which is just wrong. And that range is in the order of about, I need to read the numbers again, it was about 0.04 to 0.2 micron. And this range is just wrong because capillary suction is high. It loves to pull the water in. But the thermodynamics is such that it's really difficult to get the water to evaporate out. That capillary surface holds the water in. It's energetically preferable for the water to stay there. So the system doesn't dry out very readily. And then when we have a freeze-thaw cycle, we've got a piece of rock that's got lots of water in it. The water expands. 9%, thank you. And that's why we're incurring damage. And that leads me to one of the other questions a little earlier was, what if we made the concrete stronger? Ain't going to work. Because when you've got a material putting up very high stresses internally, it's got to be very, very strong concrete to resist those stresses. And I don't think going to a low water cement ratio and making 6,000 psi concrete is going to make a whole lot of difference in this environment. Okay, so the pore size is pretty typical. Wendell actually produced quite a lot of data showing materials that were problematic had a fairly characteristic plot. Materials that were less problematic had a different plot. Just out of interest, I ran the same test on 0.4 water cement concrete. Guess which line it followed? The bad one. Oh dear. The difference being is that in 0.4 water cement ratio concrete that we know is going to be freeze-thaw, we put air bubbles in. And that changes the rules on us. But that's fundamentally why concrete struggles, because pretty good structural pavement concrete without air in it has got the same pore size distribution as deep cracking prone aggregates. Okay, we had a limited number of data points. We managed to get a paper published. I still have to do some more work to nail that one down a little bit more. All right. So the three parameters that the DOT uses, it's not just the size. They look at the clay content of the aggregate. They look at the pore solution, the pore size, and they also look at the limestone dolomite balance. So how much magnesium do you have in the system? And they come up with what they call quality numbers. And they do a weighted system on which quality number matters the most depending on where it sits in that limestone dolomite scale. And I'll get to that a little bit later. So the first parameter that they're really excited about, alumina. Why? Because all clays contain alumina. So you can run an XRF and pick up what is the alumina content of the material. And I think that's the basis of what you were talking about, Heather, is if you're going to characterize an aggregate at its point of delivery, that ties in quite nicely with what we're doing here. So again, pretty simple stuff. They've got a fairly good correlation between clay content and alumina content. And again, they've come up with the historical data on if you have an alumina between 0.3 something and 0.6, it's not so good. And if you've got less than 0.25, it's really good. So they've classified the aggregates based on the alumina content. Then there is the Iowa Pore Index test, which Heather alluded to a little earlier. Interesting approach. Basically, you take a sample of the aggregate and you squeeze a bunch of water into it. And you measure how much water goes in 2 minutes or 1 minute and how much goes in 15 minutes. And so you get two different numbers, what they call the primary and the secondary. The critical one is how much water goes in over a fairly long period of time at fairly high pressure. Not too many of these devices floating around, and it actually hasn't found a lot of acceptance by other DOTs, including Kansas. I think you guys play with it, but you don't really use it. And so, the Iowans love it. They think it works. Still got to sell it to everybody else on the planet. There are not too many of these toys around. The DOT has one, and I borrow it occasionally. But again, what it's doing is using how easy is it to push the water into the concrete to get a handle of that pore size distribution. And again, they've come up with these quality numbers based on the different numbers that are coming out of the test. So again, we're qualifying it as to what is good, bad, and not so good. Then they use X-ray diffraction. This is the gain that they use to quantify where the material sits on the limestone dolomite family. For those who don't know, again, I'm a dumb engineer. I had to be taught this pretty carefully. There's pure limestone, which is calcium carbonate. Then there's dolomite, which is calcium magnesium carbonate. And the amount of magnesium in that system varies between none and a lot. I don't know, geologists, help me. How much can we get in there? No one's answering. Okay. So, it's not like there's a distinct, this is a dolomite and this is a limestone. It's normally a jumble of the two different compounds. And so we are talking about a variable system that we're trying to get a handle on. And again, if you run XRD, you get a limestone peak, you get a dolomite peak, and under certain circumstances, you can get a bit of a shift. And it's that shift that we're interested in. Is that the bigger the shift, the worse off the material is going to be. Tied to that is other chemicals that may be in the system, sulfur, manganese. The more there is, the more. These are the compounds that are going to react with the de-icing salts. So the sensitivity to mag chloride, calcium chloride, even sodium chloride is tied to these other contaminants in the system. Rock is not a pure material. And other stuff. Okay. Then there is the issue, okay, we've now got these three quality numbers. We've got the XRF, we've got the pore index, and we've got the XRD-based numbers. Which one's most important? And the answer is it all depends. If you have something tied on the limestone end of it, the XRD side of it is not that critical. And so then it's a pretty equal balance between the pore index and the clay content as being contributors to the risk of deterioration. If you're at the high end of the dolomite end of the scale, the XRD is critical but not so much, and again, balancing out the other two parameters. If you're at that intermediate dolomite, 10% magnesium, then the XRD is probably the most critical parameter within the system. So it's a graduated scale depending on the system that you're dealing with. So what they do, they go to the quarry, they core it in advance, and they have then a classification of the different ledges. So here we've got various grades of what looks like a class 2. That's a 20-year system. And then it becomes a certification of, is this material in this bed the same as the stuff that we sampled and approved, or at least classified in the past. And so the DOT has an ongoing process of ledge inspection, ledge pre-qualification. And that's how they think they've got a pretty good handle, is that they pull the cores, they run the suite of tests, they identify, this is good stuff, go mine here. And that's how we have a handle of it. So the DOT has this pretty convincing story. They do a bunch of tests, they pre-qualify the quarry, and we think we've got a pretty good story as to what is reliable and what is not. And it is convincing, is that the DOT has very little distress in their system of pavements that have been placed since they instituted this program. Likewise, many of the cities and counties that follow the DOT processes seem to be in pretty good shape. And in fact, it's proving interesting. I wanted to get out there and get photographs of failing decracking pavements. And there weren't so many, mainly because all of the bad ones have been covered up or replaced already. And there's nothing that is relatively new that is showing a lot of distress. The exception is privately owned facilities, the sort of place Tom was talking about. Gas stations are the worst. They are horrible, and that's because they're buying the cheapest stuff and it's not getting inspected. All right. I did want to pick up one or two other points. The idea of the small aggregate, it's what we wrote about for years. The IMCP manual, we said 3/4 inch, 1/2 inch, go smaller. I'm beginning to think that all that did was buy us time. I recently went on a site of a county street. The county engineer was pretty grumpy because his whole system was falling apart. Turns out that the whole county paved all of their system in a space of 3 to 5 years in 1970. They followed the rules. They said 1/2 inch to 3/4 inch coarse aggregate maximum size. They are in the southwestern corner of the state, which has problematic aggregates. It worked. They got 40 years out of that pavement. But now it's starting to go, and the cores look just like the one that Tom just passed around. Horizontal cracks near the surface. Okay, because the water has got to it, it's been saturated, frozen, and over 40 years. Being small, it's taken a long time. But it is still starting to fail. So going small is not a bad idea, but it's not the sole answer. It buys us time. That's where I'm coming to right at the moment. So where do we go next? I'm starting to fool around with another test. You know, the Iowa Pore Index test. You need a fancy machine. You need lots of water. You need smart people to operate it. We're actually playing with another approach. I've got a master's student messing around at the moment with the device. It seems to work quite nicely. 10-minute test gives us an answer. I'm still collecting a lot more data on materials that we know are not so good, materials that we know are good, and I'm still trying to get some of those intermediate materials, the ones that would show up in Heather's curves of being we don't know yet. But I think we're on to something of being able to do the pore size of it pretty simply. Is there an easier way to find the clays? Do we have to go to the expense of an X-ray fluorescence test? I used to work for a lab. I know how much money we made out of that machine. I know how long it took for samples to go through the machine. well, the processing time, including 2 weeks on the counter before it actually made its way into the lab. Is there a way we can do this better, quicker, faster? Again, I think we have some ideas. The other issue we were talking about last week was, okay, I get a concrete or a bucket of material delivered to my site. How do I know that it is actually good stuff or not? If it's quartz or granite, yeah, it's not limestone. We're all good. But if I get a limestone delivered, how do I know that it's good? Is there a way that we can do a quick and dirty field evaluation to say, this is the same stuff that I liked in the quarry? I've heard this from other states. Michigan have been talking to me and saying, yeah, we do our quarry pre-qualification. That all works really nicely. But do I know that the stuff that's been delivered came from this ledge? Or did it come from somewhere else? We need those sort of tools. So there is still some space for some fundamental research.